So I will draw a basic AC to DC rectifier. Then we will analyze what is rectifier and its operation. So do you know what is the objective of rectifier in power electronic circuit? Anyone? Okay, so this is the switch H1 here. And first, let me tell you what is rectifier, what it does. So our objective is that we give AC supply. The supply is generally AC, and we want DC load. We need to cater this load. For that purpose, we need DC components at the output side. So I think someone had message. AC to DC conversion. Right, right. You are correct. So this is the objective. How much we achieve by this operation of switching, that we will see. Okay. So this we have objective that we should get pure DC output. Okay. With pure AC supply. Now, since we know that our switches has inherent characteristics of to provide not pure AC or DC, right? It will never provide you pure AC in case of inverter also. In case of DC to DC converter, we have also saw that there were no pure DC component. We were getting some ripple there at load side. So there also not pure DC we were achieving. In rectifier, we will also see what is the issues and how can we cater those things. Okay. So uh, let us suppose, let me draw the switching pulses here. So this is a typical pulse, what we are providing back from inverter. So we assume this duration to be, dt, and t is generally 2 pi, so 2d into pi, right? And if I write the instant of time in angular terms, let me take in omega t. So it will vary from minus d pi to d pi, and its magnitude will be 1 for simplicity's sake. And if we multiply directly with Vs, it will be Vs for this period, right? Now, this switch is in a square form, right? It is rectangular pulse. So, but we want sinusoidal. Okay, all we want DC at output, and we want AC or pure sinusoidal at supply side. But we will get or not, we will see, because I have already derived the expression of switching function, that was d plus n is equal to 135 up to infinite. And with this approach, you can see, or you will be able to visualize the Fourier series in just one or two steps. Right? So that we will also see in later stage. This was the expression I derived: 2 by n pi sine n pi d cos n omega t. Now, we want DC at this stage, and I told you, if we want to calculate voltage at this node, let us suppose this is V node, we will get in terms of H1 into Vs, right? Just the basic multiplication of the switching function with supply voltage. We will get H1 into Vs. Now, from H1 expression here, from H1 expression, we can see It has D, which is purely integer, or you can say in DC component, as well as you have some AC components. So again, you will get at output side, you will get definitely DC component, but you will have to manage with some AC components, which is known as ripple. Okay, how much ripple will be there, that you can easily calculate with this formula, right? You put the different value of n, and then you can easily compute that. So this is the problem with rectifiers. And also, if you have, you might have seen that there are certain supplies. Let me take a typical example. So this is the kind of voltage supply is given, and if you are doing full wave rectification, right, single phase, let us assume for time's sake, so you will get something like V naught, something like this. Okay, so just tell me, is it desirable to achieve this kind of output voltage waveform, or is there any flaw with this kind of waveform? Okay, so I don't think we need this kind of waveform of output voltage. What we need, we simply want this kind of waveform, right? We do not want this ripple. This is basically ripple you are getting with del V naught. As we saw in DC-DC converters also, there was some ripple in capacitor voltage, or you can say in output voltage directly. So these are unwanted components. So our objective is to minimize it as a designer, to minimize this ripple, and we should be able to get constant DC component. But it is a bit difficult. So I just wanted to, visualize what are the problems. These are not desirable things, but we have get used to of it, of achieving this kind of waveforms and getting DC components. So moving ahead now, to get V naught, I will write H1 into Vs, and H1 expression is written here. So you will get dVs plus into 135 up to infinite 2 by n pi sin n pi d cos n omega t with Vs. Okay, and Vs, let us assume, since we are taking here the even function, so I will go ahead with Vs is equal to Vm cos omega t. However, generally people deal in terms of sin omega t, but I will take cos omega t. Nothing much difference, just the shifting of pi by 2 is there. So if I put Vs is equal to Vm cos omega t, you will get dVm cos omega t plus your Vs into, sorry, Vm into cos omega t to 2 by pi, I can write here 1 by n sin n pi d cos n omega t. Okay. So another issue arises here. Do you see what is the issue in this expression? Because I am not able to see any DC component in this expression. Okay. I'm sure you also would not be able to see any DC component. Because I multiplied just d with Vm cos omega t, I will get d Vm cos omega t, and generally d is like half, so Vm cos omega t by half. So this is AC component here. These are also cosine functions, so these are also AC. So you will get DC for a particular condition, and that condition is when n is equal to 1. Okay, when n is equal to 1, if you put in this expression, what you will get, v naught 1, let me write it, Vm into 2 pi into, I have put n is equal to 1, n is equal to 1, sin n pi d, sorry, n is cancelled here, sin pi d cos omega t, and this cos omega t also I am considering here, cos omega t. Now you can see that some DC component may come, right? 2 Vm by pi sin pi d cos square omega t, right? So that will be 1 plus cos 2 omega t by 2. Am I right? And now if you segregate these components, you will get 2 Vm by pi sin pi d into half. So let me multiply it with half plus 2 Vm by pi sin pi d. If you are not getting at any step, please feel free to stop me at any point. Okay. Into cos 2 omega t by 2, right? So Vm by pi. Now you would see that these are kind of familiar terms, Vm by pi to Vm by pi, kind of terms you must have seen somewhere if you would have studied. So Vm by pi sin pi d plus Vm by pi sin pi d into cos 2 omega t. So now you can observe that just taking a single condition, right? We took just n is equal to 1, and we are getting a component or a magnitude of DC, which is Vm by pi sin pi d, and the ripple magnitude is also same for this, right? This is the ripple magnitude here, and ripple magnitude should not be like greater than your DC component. Otherwise, your voltage ripple factor or ripple factor would be very high, and that would not be suitable for any rectifier. So these are the problems what I wanted to share. Just taking consideration in one term, I just took n is equal to 1, and I am facing this kind of ripple problem here. And later part other factors, if I put n is equal to 3, 5, you would not get any DC component at all. And again, this component is already there, dVm cos omega t. Okay, so like ripple components are way higher than your average components. So that is the issue with this kind of output voltage waveform, right? Any doubt in this? I can go back and explain again if you want. Okay, no doubt. Thanks, Apurva. So we are basically, concerned with DC component. So we will go ahead with this DC component, right? And I will write V naught in terms of Vm by pi sine pi d. Now you would be thinking that why I am carrying this baggage of pi d and all. Because if you see your DC voltage at output for half wave rectifier, what is the expression of voltage for output voltage for half wave rectifier? Just let me, you know, mm, if you integrate, let us assume this is a half wave rectifier. Okay, so this is kind of waveform you will achieve at output, and if you need, you can easily derive what are the average voltage of half wave rectifier. Average is nothing, just the area of the in your graph, right? In one time period. So from 0 to 2 pi, however, the signal is still pi only, right? Here this is 2 pi, 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 2 pi. And your supply is Vm cos omega t. Sorry, here sin omega t it is, right? So Vm sin omega t d omega t. And if you integrate it, Vm by 2 pi, integral of sine is cos, so 1 minus minus 1. So that is Vm by pi, right? So this is average value of your output voltage for this half wave rectifier. And this switching function, we did such a tedious task to arrive at that conclusion that it is Vm by pi sine pi d. And here d, if you can see, d is nothing but the pi, right? Why I am saying d is pi? Because switch is conducting only for pi period, right? After that, switch would not conduct because we want the operation of half wave rectifier, and if it is a unidirectional switch, like diode or MOSFET or IGBT, so it will not conduct in negative cycle, right? If you give supply of Vm sin omega t, and if your supply is going in negative direction, if your supply is going in negative direction, this switch would be in reverse blocking mode, and hence it will not conduct after pi. So that's why its duty cycle, if we write in terms of integer, it will be zero point 0.5 only. Now I will plug that d is equal to zero point 0.5 terms here. Zero point 0.5 means pi by 2, right? So it is Vm by pi sine pi by 2, and that is your Vm by pi. So we did all the derivation to arrive at this point. V naught is equal to Vm by pi for half wave rectifier. However, that was not needed, but that was required to get insight of this kind of converters, like how much rectifier. Now you can easily, with this expression, right? With this expression, you can easily calculate any number of ripples. Second ripple, third ripple, fourth order of ripple, any ripple, right? You just need to plug the value of n is equal to 1, 2, or 3, or 4. That's it. So I hope it is clear to you. Now let me proceed with full wave rectifier. Okay, so it would be better because most of the converters are full wave rectifiers only. What is the problem with half wave rectifier? Um, One problem from this waveform you can easily identify, right? This waveform, that it is not conducting for entire period until and unless you are providing very high inductance in your load circuit. You will not get conduction continuous, right? And that might be issue for many circuits. So that is one issue. and your output voltage is also very less at Vm by pi. And if you might have studied full wave rectifier, you will get output voltage 2 Vm by pi. Okay, that we will see in coming session. So let me draw the full wave rectifier circuit here. H1, H2, H3, H4. Okay. Now this rectifier is connected to some load. Vs. So just let me clarify the operation of switches in this kind of circuit. So if Vs, let me also write the polarity, and let us consider Vs is equal to Vm sine omega t. Okay. Now this sine omega t term would be positive. Okay, for 0 to pi duration. From 0 to pi, Vs is positive, and from pi to 2 pi, Vs is negative. Now, if Vs is positive, your positive terminal node will be at this point at node 1, and negative kind of thing would be at node 2, right? And typically, if I just draw in terms of any switch, let me take the case for diode. So if it is diode is connected in this fashion here, here also, this is a typical full wave uncontrolled rectifier. Okay. Now for 0 to pi, this diode anode terminal is seeing this positive thing, and it will be in forward conducting mode, and this diode 2 H2, this is observing this negative terminal at node 2, and its cathode is connected to negative terminal, so it will be forward biased. So for 0 to pi duration, your H1 and H2 will conduct. H1 and H2 will conduct. Similarly, from pi to 2 pi, this Vs will be negative now, right? Now, negative node of voltage is appearing at node 1, and since H1 anode is connected here and H4 cathode is connected at node 1, or you can say pole 1, right? So at pole 1, this negative voltage is appearing across this cathode of diode, and hence H4 will be turned on. And again, this positive thing will be appeared across the anode of H3, and your H3 will be turned on, right? So this is kind of operation for some uncontrolled rectifier, full bridge single phase uncontrolled rectifier. So that just I wanted to clarify here. Now we will see what are the nature of conduction and all. So again, I will write switching function because I like switching function very much. So I will write it again. 2 by pi n is equal to 135 up to infinite 1 by n sin n pi d cos n omega t. Okay. This is the switching function I have decided for h1. Okay. I am considering the pulse for h1 is this one. This is the pulse for h1 I am considering. Okay. What I drawn at the starting of the session. So this is the pulse for h1 I am considering here, and I can write the switching function for this pulse in this terms of h1, right? Now, what will be the switching function for h2? Could anyone let me know what will be the switching function for h2? Just in terms of shifting or same, or it will be some other something other. You do not need to specify entire expression. Just make it, you know, bit what to say. Okay, so I think you guys are not comfortable in speaking, so I will tell it. H2 switch, this H2 switch will be same because whenever H1 will conduct, H2 will also conduct because these two switches are simultaneously forward biased mode, right? So they will conduct simultaneously. So H2 switching function will be similar to H1. So it is simplifying our life, right? We can use same thing. And just I want to let you know the expression for V naught, right? That is very important. V naught and I naught, because ultimately we will be asked to calculate V naught and I naught. So V naught, if I want to write, okay. So when H1 and H2 will conduct, so the circuit will look like something kind of this. Mm, yeah. Okay. So here H1 was there and H2 was there, right? Yes. Someone want to speak something? Please go ahead. Okay. Fine. So when H1 is conducting and H2 is conducting, you will get V naught is equal to, you know, H1 Vs or Vm sin omega t, or it is equivalent to H2 into Vm sin omega t. Okay. If they are off, let me open these switches. So now they are open. So no any voltage would appear in terms of H1 and H2. Then for pi to 2 pi, Other switches H3 and H4, as I mentioned, they will be conducting, and here it was in this polarity. So now H3 and H4 is conducting. Okay. So H3 was here and H4 was here. Now I can write it V naught as H3 Vm sine omega t or H4 Vm sine omega t. Okay. And H3 and H4 we need to identify. Okay. And from waveforms, we will be able to visualize that it is shifted by pi from H1 and H2. However, this signs would be in negative. Why so? Because I have conveniently reversed the polarity here. Okay. But in general circuitry, I need to stick with a single polarity, particularly in AC components. So if I am stick with this kind of polarity, then this is minus here, right? So I need to include minus to account that reversal of your polarity, because these values are changing in your waveform, but you need to write it in a single expression. So for that, you need to take consideration of these polarities. So this will be, I write in terms of minus. So if I club all the things to come at a single expression of V naught, so that will be H1 Vs, that is sine omega t, minus H3 Vs. Okay. So this will be your output voltage for a single phase full bridge rectifier. Okay. So this thing, even though I did all these things, you can write it in single expression just by seeing the circuit here. V naught, if V naught is connected with H1 and H3 also, right? You can easily see V naught is connected to H1 and H3. If H3 will conduct, H4 will conduct. If H1 will conduct, H2 will conduct. So you can write V naught directly. V naught is equal to, by just observing, as simple as DC-DC converter or any other rectifier I explained earlier. So it will be H1 Vs minus H3 Vs. That's it. So you will get your output. Now the exact value of output voltage, that you need to do a bit calculation here, and that is also easy. I will go ahead and I will explain that also. So this is the basic thing what I wanted to explain for output voltage for your single phase full bridge rectifier. Now I need to find out the expression for H3, although I have derived in my inverter lectures. So here I will do the same. I will just shift it with pi, right? So H1, let me copy it. So this is the expression of H1, right? Now I want to write H3. It will be same. And yeah, mind it, H1 is equal to H2 and H3 is equal to H4. T plus 2 by pi n is equal to 135. Okay, one more question. Why I am taking only 135? Why I am excluding even components of your switching function? Any guess? So I am doing for the purpose of, if you put generally d is equal to half, okay? And if you put d is equal to half, and if you take n even, so it will be in order of sine 2 pi, 4 pi, 6 pi, and all sine of 2 pi, 4 pi is 0. So that terms will be 0. So just to clarify that, I am writing only odd terms. Otherwise, you could have simply written it in this manner. That would also be fine. Now, we have arrived with the switching function of h1 and h3. Now we need to compute the value of output voltage. And I can write cos n omega t minus pi, just to simplify, minus 1 raised to power n into cos omega t, cos n omega t. Okay. So when n is odd, this component will be negative. For n odd, this will be negative. If n is even, this component will be positive. So it will reduce your time in computation. Now we have written V naught is equal to H1 Vm sin omega t or cos omega t, doesn't matter. So let me take, since I am dealing in terms of even switching function, so let me take the supply for full bridge rectifier in cos omega t, okay, minus H3 Vm cos omega t, where Vs is Vm cos omega t. Okay, that is another reason why people generally use sin omega t in supply. I am taking here cos omega t in supply for the reason I am taking these pulses starting from uh, minus d pi to d pi. So I am making intentionally this switching function even. Okay, where it went. Yeah. So I am making it particularly, intentionally it even, so that if you find out the Fourier series, you will get something like this. And if you multiply with your supply of also cosine, so this is the curve of cosine, and fundamental of this pulse you will also get in terms of cosine. So cosine and cosine multiplication will give you DC and second order ripple. So that's the purpose here. Now, what people do, they take this kind of switches, I mean, in terms of odd, and then they will give, you will get some Fourier series of this kind of pulse in sinusoidal. And if you provide supply also in form of sinusoid, then again, sin omega t and sin omega t, you will get fundamental and ripple of second order. So I hope you understood the reason behind why I am going with cosine, because I have considered even function already. So now I need to provide cosine kind of supply. Okay. So does that make sense? Now I will write all the things. H1 Vm cos omega t is constant into H1 minus H3, and if I want to write H1 is d plus 2 by pi n is equal to anything 1 by n sine n pi d cos n omega t. This terms corresponding to H1. Yeah. Just don't get scared with this kind of bulkier expression. It will be simplified to really easy components. It is nothing that I am making it a bit complex and then I am explaining it. It is just for the sake of making it bit understandable and easy. Now, if you see here, your dominant component of ripple, that is nothing but fundamental or first ripple, that will get eliminated from this expression itself. Okay, how this d and this d will get cancelled, and in half wave rectifier this was not the case because this there was only h1 present. Here I am doing h1 minus h3, and due to that this both fundamental dominant ripple is getting reduced. So that is another advantage of single phase full bridge rectifier. Your dominant first order ripple is getting eliminated. Could you appreciate this point of single phase full bridge rectifier? Okay, this is the major advantage. Now, again, if I want to compute DC component, because in rectifier we are just concerned with DC output voltage, nothing else. For that thing, again, I have to, let me just write it again, club it all these things. V naught is equal to Vm cos omega t. I will take 2 pi also, 2 by pi, sorry, common. And now I will write n is equal to 1 to infinity 1 by n sine n pi d. These components are also common. Okay. Now the left thing is cos n omega t. Oh, sorry, I left it here pi. Cos n omega t minus cos n omega t minus pi. Now, again, as same as half wave rectifier, what we need to do it here to achieve only DC component. So which component of n I should consider? Okay. I will mention my YouTube channel name. Just let me write in chat box. It is JDS at the rate IITB. Okay. You can see there all kind of things. So coming back to this question, V naught, to get only DC component of V naught, which component of N I will take? It will be similar to as half wave rectifier. It will be N is equal to 1. So If I put n is equal to 1, then we will get V naught in terms of 2 Vm by pi. Now it is conversing with our initial knowledge. 2 Vm by pi cos omega t into sin pi d into cos omega t minus cos omega t minus pi. Okay. And this cos omega t minus pi will be minus cos omega t, as I told you. Cos n omega t minus pi is nothing but minus 1 raised to power n into cos omega t. So it will be equivalent to cos omega t minus minus cos omega t, that will be 2 cos omega t. And here we go, 2 Vm by pi sin pi d into 2 cos square omega t, and we can write 2 cos square omega t in terms of 1 plus 2 cos omega t divided by 2. So I will simplify it further, sin pi d into 1 plus cos 2 omega t. Okay, so now I can easily extract the DC component. This term will give you DC, and this will again second order ripple. So V naught is here, just average of V naught is 2 Vm by pi sin pi d. And as I mentioned that d is generally provided, like one switch will conduct from 0 to pi, means d will be half. So again, if you plug in the value of d is equal to half, so you will get sin pi by 2, and that is nothing but 1. So again, you end up with V naught average of 2 Vm by pi. So this is, I guess, known expression for single phase full bridge rectifier. Okay. This I could have derived in just one step, but I just wanted to, let you know what all things going behind this rectifier operation, so that in future you do not get stuck in any interviews and all. So this kind of stuff would be very useful, and this kind of things you can apply just with the, V naught is equal to H1 Vs minus H3 Vs. You can just move forward from that in a smooth manner, and you will end up with this kind of things. Okay, so we computed V naught average value. Okay. Now I want to write Is in terms of, we wrote V naught in terms of all the ripples and all those things, average along with all those ripples. Now I want to write the Fourier series of our Is, source voltage. Why Fourier series for, sorry, source current? Why I need to write down the Fourier series of source current only? Why not other parameters? Why only source current? So for that thing, I will provide the reason here. Okay, so just let me bring the circuit back. Yeah, here it is. So this was the circuit there. So let us assume that you have output current almost DC. If you have output current almost DC, it means your I naught would be flat. I'm assuming this will be in ideal case. Of course, you know that there will be ripple in output current, but for gate scope, they are, basically limited till constant DC component. So most of the times you will face only constant DC component of I naught. And if I naught is purely DC, let me take a instant 2 pi and pi, then you will get IS. Okay. Let me consider this polarity plus minus. So when H1 and H2 was conducting, okay, then your current was going in this direction, okay, in this manner. It was going to the load and all the way through H2 again back to supply. Okay. So if I am considering this as a positive, IS as positive, now during negative cycle, what will happen? H3 and H4 will conduct. H3 and H4 will conduct. Now the circuits were connected in this fashion. So now current has to flow in this manner because DC component you cannot change, and you are doing that variation in switches. So now your current will go in this fashion from H3 to I naught to H4. Okay. And now the direction of IS is reversed here. So till pi, Is was equivalent to I naught, but after pi, when H3 and H4 was conducting, then you are getting negative value of I naught. So here the magnitude will be I naught and minus I naught. So now it is a full square kind of waveform, and it will give you certainly AC components here that will be dominant. And as we you might have seen, no need to worry about the values, but you will get kind of 4 I naught by pi of fundamental. Right? Fundamental here, I mean first order of frequency. 4 I naught by pi sine omega t kind of thing. So that will be uh, the magnitude of this current, fundamental. And in next session, we will see the distortion factor and all those parameters, what we are concerned of. But here, why we are getting this kind of waveform here? Just let me clarify. So we want dominant component of sinusoidal. Okay, that is desirable. That is at max you will get sinusoidal at input. Okay, just let me again tell you that Vs is equal to Vm sine omega t. And ideally, if you use very high filter inductance at input side, generally which is connected, so at max you will get Is equal to Im sine omega t. Okay. After this point, you will not gain anything. And even after this point, power from input side will be Vs Is, and that will be Vm Im sine square omega t. Okay. And we all know sine square omega t is nothing but 1 minus cos 2 omega by 2. So Vm Im by 2, 1 minus cos 2 omega t. So now you can see we are getting a DC component of power. Okay, this is DC component of power. But again, we are getting some, second, second oscillating component of power, second order of oscillating component of power. So, and that P input will go to your P output for the ideal condition. And for that thing, you will get Vm Im by 2 as power that is desirable. Okay. But even in ideal case also, you will get P is equal to Vm Im by 2, same magnitude of cosine 2 omega t, second order of oscillating ripple. So again, so this is another drawback of single phase rectifier. That's why people went to three phase rectifier, right? So in single phase half wave rectifier, there was drawback that our DC component was not so much high. It was only Vm by pi. Okay. Single phase half wave rectifier, V naught was Vm by pi, but full bridge rectifier or full wave rectifier, we got 2 Vm by pi. Okay. Another component in single phase half wave rectifier, our first order ripple was very dominant. Dominant. Here, first order ripple got eliminated. So this was the advantage, basic advantages. There are certain more advantages that you can find in some textbooks also. So these are the advantages, which is salient features of these converters. So I will derive Fourier series of this current waveform really easy manner with the help of again this switching function in just one or two steps in next session. Okay, so that we can carry on forward from this point in next session, next Thursday we will again meet. Okay, so I hope it is clear. Again, if you have any doubt, please feel free to ask. And so just make the session a bit interactive, so that I will also get your input, like where I should work or what I am not delivering, what you should get. So those kind of stuff, if you are able to let me know, then please let me know by message, by chat, or by here also. I will write my email ID in chat box so that you can reach to me at any time. But why we are also using half wave rectifier? Yeah, of course, that is a good question. In half wave rectifier, you are done with single switch. You do not need more than single switch. And switches had some cost, right? That will be major cost for any power electronics devices. Devices has higher cost. And your gate exam is also coming really soon. I think there are 1 to 1.5 months left. So just start accelerating your preparation, and any issue you want to discuss, we can discuss anytime, or any particular topic in power electronics or machine you want me to cover. I can do that if you are interested in that. So Saurav, yeah, I gave answer to that your question. Yeah, thanks. Thanks, Saurav. So I think we should wind up the session here. We will meet again next Thursday. Thank you very much for joining. Yeah, thank you. Thank you, everyone. Thank you, Apurva. Thank you, Josna. Thank you, Saurav. We will meet again. Fine. Bye. Bye, guys.